We are in the second part of your medical imaging now, which is computed tomography. Where is it? This one is this one. CT scan is computed tomography. All right. So what is actually CT scan? CT scan, as I mentioned, is actually still based on X-ray, but the image that you get is a vast improvement over your normal X-ray. Okay. Now, just now I sent to you some two little screenshot or something, right? Which is this one. Okay. Now, when you're talking about CT scan and normal X-ray, one of the ways in which a CT scan would differ from a normal X-ray is that a CT scan uses many X-rays to produce a 3D image of your body. Say for example, right now, if I say that you want to do a imaging of your skull, under most cases, if you try to do an image of your skull, like say this is the person's head, you want to do an image of the person's skull. If you're using X-ray, the normal X-ray, which is done using a single exposure, the idea would be that your X-ray comes here, and then after that you will put a X-ray film behind, and then the X-ray will pass through the person's head, and then after that you will darken the X-ray film behind. So at the end of the day, the image you get is just something that looks like this. You look at the X-ray film, you see the outline of a person's skull that looks like this. Okay, and then the remaining portions of the film will just be darkened. It will just look something like this, right? Now, this kind of imaging has a drawback. The image that you get is 2D in nature. All right, you're only seeing a flat image of your skull. You cannot see the side, you cannot see the front, you cannot see the top, the back, or anywhere else. It's always 2D. Okay, so you need to have a 3D image. Okay, so you need to have a 3D image of the skull. So what you need to do is that you need to use CT scan. All right, so the problem with your X-ray now is that this one is just a 2D image. Okay, so you cannot see top, back, left, right, or anywhere else. So CT scan will overcome this. What we will tell you is that for CT scan, the image that you get of your skull is 3D in nature. You can see at different angles, you can rotate it about. So that's why we tell you that CT scan is an improvement of your normal X-ray because the image by nature is 3D. It is not like your normal X-ray, which is 2D. Okay, but there's a drawback to this kind of imaging. Your image is better, but your CT scan is actually much more harmful than your normal X-ray because of the fact that when you want to produce a CT scan, your radiation exposure would be much higher than a normal X-ray. Okay. Now, why do we say that the radiation exposure for CT scan is much higher than a normal X-ray? You have to understand how a CT scan image is built out in the first place. Okay. Now, say for example, you have a skull here like this. All right. You have a person's head whose skull you want to do a scanning of. When you want to do CT scan, what we'll tell you is that you will first divide the object that you want to scan into slices. Meaning to say what we do is that this is the person's head, we will divide it into multiple slices. We will divide it into slices. We will divide it up into slices. And then what we'll do is that we will start to take an X-ray image of one slice first. Okay, so the X-ray image of one slice, it could be that now it say right now I divide the head into multiple slices. I only want to consider one slice. This is one slice here. what we'll say is that that one slice that you have, if this is that slice right now, when we want to produce an image for that slice, we will start by taking X-ray images of that slice at different angles. All right. So say, for example, right now, you're taking an image of this one slice. You will actually have to start your X-ray image, taking X-ray image of that slice in 4 different directions. This is one direction. This is the second direction. This is the third direction. This is the fourth direction. Okay. So what I will tell you is that you take an image of one slice first. When you want to take the image of one slice, you take X-ray images at different angles in order to produce a 2D image of the slice. When you produce a 2D image of the slice, it will be in the form of numbers. The slice that you have, it will break it down into 4 square boxes called voxels, and then the voxels would have a certain value inside. The value inside the voxel represents to you the amount of radiation that has been absorbed for that particular region. It's a measure of what is contained in that slice. It helps you to build out an image of your slice. Okay. So you take the image of one slice first, where you take the X-ray image at different angles. After you have done the image of one slice, then you repeat the process again for successive slices. You go from the first slice here to this one, to this one, to this one, this one, this one, this one, this one, and this one. Okay, you repeat the process for successive slices so that you have a lot of image for all the slices. Then after that, what you do is that you combine them together. You repeat the process of scanning the slices and then you combine them together. Once you combine them together, that is how you get your 3D image in your CT scan. Okay, this is in general how you produce an X-ray, how you produce a CT scan of a human body, of your skull, for example. So the image you get will not be a flat 2D image like this. It will be a 3D image of your skull, which you can view at different angles. So the image quality is much better, but your health risk here is much higher also, because as you can see, when you wanted to produce the image of one slice, you've already exposed yourself to 4 times of X-ray. So you imagine if you have 10 slices here, 10 times 40 means 40 times radiation exposure, which is much higher than a normal X-ray. So that's why we say that it's actually not as safe as your normal X-ray, because your radiation exposure is a lot larger. Okay, that is in general how CT scan actually works. Okay, so that one is one half of your CT scan. You can have a look at page 11. Let's just do some examples first before I move on to the next part of CT scan. Okay, have a look at page 11 of your worksheet. Page 11 has something to do with X-rays for the first part, but the second part won't be on X-ray. This one is Mark 16 P42. Okay, that one will be question 12. Okay, in the X-ray tube, the hardness of X-ray beam may be controlled. What is meant by hardness of the beam is the penetration power of the beam through a medium. This one we just done something like that. That one was actually worth two marks. Okay, this is now just worth 1 mark, so you don't really need to explain as much. Then after that, state how the hardness of the X-ray beam may be decreased. You just decrease the tube voltage. You just decrease the voltage between the anode and the cathode. This one is understood already. Okay, now part B. Part B is not talking to you about comparison between CT scan image of a person and a standard X-ray image or normal X-ray image. So as I mentioned to you, CT scan image is actually better than your normal X-ray image or your standard X-ray image because the image is 3D. You can view it at different angle. Here the marking scene say the image gives you that. Okay. But what is the disadvantage of your CT scan is that there is greater radiation exposure. Okay. Because each slice you have to scan by slices. Each slice would take at least 4 exposures. So you multiply that by the number of slices you have, you can imagine there's actually a lot. So there's greater exposure to radiation, therefore more risk to health. Okay, so that one is fine. Then you can move on to the other one. The next one you can do is page 30. Now have a look at page 30. Page 30 is June 18 P42. Okay, now is question 11. Okay, now describe the basic principles of CT scanning, computer tomography. Basically, that what they're asking you is how do you actually produce an image during CT scanning? So whatever I just mentioned just now is actually kind of summarized in this statement here. Okay. Now for medical imaging chapter, you will often see a lot of times where the question asks you to describe how you produce an image using X-ray, how you produce an image using CT scan, how you produce an image using ultrasound, using MRI. It's like a mini essay question with quite a significant amount of marks allocated. So the good news for you is that these questions are usually repeated year in, year out with the same set of answers. So if you memorize the sample answer and the questions come out, a lot of times you'll be able to score almost full marks, if not full marks for the question itself. So it may work best for you if you have prepared well for this chapter. But if you did not prepare well and you did not memorize, then this kind of question will be really bad for you. Okay. Now, describe basic principle of CT scanning. So as mentioned, X-ray image of one slice is taken at different angles. A computer produces a 2D image of the slice. The process is repeated for many slices to build a 3D image of the structure. Okay, so this is the simple answer. You say X-ray image, 1 mark. One slice at different angles, another mark. Then after that, to get 2D image of slice is 1 mark. Process repeated for many slices, 1 mark. Give 3D image, another mark. So despite the fact that they give almost half the page for the answers, the points is only just these 3 sentences. So it's actually quite rewarding to do if you know the points. All right. So this one is the simple answer. Okay. Then after that, if you're fine with that, you can just have a look at the next part first. The one below your current question. Okay, so I assume this one is okay. Then I just move on a little to the bottom. Okay, if you look at the other part of the questions, they tell you, with reference to your answer in A, suggest why CT scanning wasn't possible before fast computers with large memories were available. Why is it that before you had computers, you cannot do CT scanning? Now, as I mentioned to you just now, when you do CT scanning, you had to do image of one slice. And then for one slice, you have to take X-ray at 4 different directions. And then after that, what you had to do was that you had to repeat the process for many successive slices before you combine them together to give a 3D image. So this process where you do a lot of X-rays for one single slice, and then after that you repeat it for many other slices before combining them, actually requires a large number of calculations. So before this, you weren't able to do so because the computers weren't powerful enough to do large number of calculations. Combining images involves large number of calculations for CT scans. If you do not have fast computers, you cannot do this. All right. So that time it wasn't possible to do CT scanning. But now with fast computers with large memories, you can do CT scan because it's able to help you combine images with large number of calculations. All right. Then for 2, they ask you why is the radiation dose for CT scan much larger than the X-ray image for a lab board? Because CT scan consists of many single X-ray images. You can imagine again that is what I say here. This is one single X-ray exposure. This is the second, this is the third, this is the fourth. And then you repeat it for all these slices. So it has many single X-ray images. So it is having a higher radiation dosage. Okay. Let's go to the last part of your CT scanning. Alright, so for CT scanning just now, as I mentioned, you want to build up an image of the slide or of the structure in 3D, you need to start by scanning a slice. And then when you start by scanning a slice, you will actually divide it into smaller sections called voxels. If this one was the slice viewed from here, this is how it looks like. And then they divide it into 4 boxes called voxels. All right. So the values inside each of those voxels will actually give you a measure of the image. It will give you some from the values contained inside the voxels. It allows you to build out a 2D image of the slice in the first place before you repeat the process for successive slices and then eventually combine them to become a 3D image. So your syllabus requires you to know how you calculate out the values inside the voxels. Okay, the values inside the voxels of a slice, sometimes they will call it voxel reading, sometimes they will call it pixel reading. So you need to, at the very least, know a bit how does CT scanning arrive at these values when they do a CT scanning. So I'll just start with the examples that you have in your notes. Okay. Now, when you want to do CT scanning, as I mentioned to you, you will start with taking an image of a slice. When you want to take an image of a slice, you take X-ray images at different directions and different angles. Say this one is one slice right now. You want to scan, say this little green thing here with the 4 small boxes with the question mark inside is a slice that you want to scan. All right, but you do not know what is the value inside each of the voxel. So when you do CT scanning, when you want to scan a slice, you actually trying to find out what is the number contained inside each of these voxels. When you first start to scan, you do not know what is the number contained inside each of these voxels. But by the end of your scanning, after you scan in 4 different directions, you will be able to find out what is the actual value. Okay, so say for the example right now, I tell you I want to scan the image of a slice with values of 4127 inside. Okay, when I want to scan it in the first place, I do not know what is the value inside. So how do I arrive at the actual value is this. So what they do now is that they will first start scanning your slice in 4 different directions. So I start scanning in the first direction here, from left to right. Okay, so this one is the slice that has this value of 4127, but I just do not know this one yet. What you do is that you will scan X-ray in this direction, and then after that you find out how much X-ray has been absorbed in this direction and this in this direction. This one 4 plus 1 will give you 5. 2 plus 7 gives you 9. So this one here, what you do is that normally when you want to scan in these 4 different directions, you will have a X-ray transmitter, and an X-ray detector. This one will transmit X-ray. This one will detect the X-ray that has passed through. So what this one here is trying to tell you is that it's trying to detect how much X-ray has been absorbed in a particular direction. So this one, it tells you that 5 has actually been absorbed. This one tells you 9 has actually been absorbed. Okay, so now they will use this value and store it inside memory first. Okay, the computer that is used to scan this image right now, they will store this inside memory. The 5 plus 9, they add it inside an imaginary voxel or imaginary slice. They say that this one will be 5, this one will be 5, this one will be 9, this one will be 9. So they first store this as 5, 9, 9. This is what they have right now, the image of the slice in the first scanning. Okay. Then after that, what they do is that after they're done with this one, they will move the scanning direction into another direction. Maybe rather than scanning in the first direction here, they now scan in the second direction here like this. So when they scan in the second direction here for that same slice, again, your X-ray transmitter is here. Your detector is at the opposing end. The detector will actually try to find out how much X-ray has actually been absorbed in this direction again. So this one, you see that this one will give you 1. This one will be 7 plus 4, giving you 11. This one will just be 2. Okay? Right? So what you have now, they add out to the image of the slice in their memory. Remember just now when you first scan this one in the first direction, they actually store these values inside the memory. In the first direction where they scan, this is the image of the slice stored in their memory, 5599. So now when they scan in the second direction, this new reading is now added to the image of the slice in the computer's memory. So 2, 11, 2, they add up to what they store in the memory. How they add it out is, you see this one will be 1 plus 5, giving you 6. Then this one will be 11 plus 5, giving you 16. 11 plus 9, giving you 20. And then for this one here will be 2 plus 9, giving you 11. Okay, so your image has now been updated. It is no longer this one. Instead, it is now this one. It is now 16, 6, 11, 20. Okay, so now you have scanned the second direction already. You now move on to the third direction. So when you want to move on to the third direction, you will be moving to here. So say now you again move to the third direction where you repeat the same process. When now this one is your X-ray transmitter, this one is your X-ray detector. Again, same thing as before, you try to sum up what is the total detector readings in a particular direction. This is 7 plus 1 giving you 8, 4 plus 2 giving you 6. So now you have 6 and 8 here. Again, you add up to what has been stored in your memory. Your memory has stored the image of a slice as 16, 6, 11, 20, right? So the 6 and 8 here, you add it back up in the same direction. If you're scanning in this direction, you add them back up in the same direction. So what you do here is this. Anyway, maybe I shouldn't wipe this one off. Okay, so what you do here is that 6 plus with 16 will give you 22. 6 plus with 11 will give you 17. 8 plus with 6 gives you 14. 8 plus with 20 will give you 28. So now your image has now been updated to this. It's no longer this one, but now it is this one now. This one will be 22, 14, 17, and 28. Okay, so the third direction has been completed. You will now move on to the fourth direction. Okay, you will now move on to the fourth direction, which is here. Okay, so same thing again. Now you add out your total detector readings in that last direction. If your transmitter is here, your detector is here, what is the total in this direction? 4 will give you 4 here. 1 plus 2 will give you 3 here. 7 will give you 7 here. Okay, so from there, once you have this one, you again add it back up to what you have stored inside your memory in the same direction. If you're scanning diagonally, you need to add it diagonally to what has been stored inside your memory. So this 437, you add it diagonally to what you store inside memory. So this one will be 4 plus 22, maybe I use a different color. This one will be 4 plus 22 giving me 26. This one will be 3 plus 14 giving me 17, 3 plus 17 giving me 20. And then lastly, this one will be 7 plus 28 giving me 35. So again, this one is no longer it's no longer updated. This is no longer the current one. The new reading would now be this. So the new reading is now 26, 17, 20, and 35. Okay. Now, this is not yet the final reading of the slice. The actual reading of the slice is 4127. So this one is not yet complete. How do you get from this to this? If you want to get from this to this step here is very important. You need to know this step. You need to memorize this step. Whatever you have here after summing in the 4 different directions, what you will normally do is that you must minus off the background intensity. Okay, your case here is that the background intensity is your total of your detector readings, which is 14 in this case. What do we mean by that? Background intensity is the total detector readings in each direction. If you just look at all the different directions that we've scanned, the first one was this one, right? If you look at your detector readings, this one will add up to become 14, isn't it? This is in the first direction. If you look at the second direction, which is the one diagonal here, look at your total detector reading again. 2 plus 11 plus 1 is also again giving you 14, isn't it? Right? Then after that, you look at the third direction, which is this one. 6 plus 8 will give you 14. Then you look at the fourth direction, the last direction. If you look at your total detector reading again, it will also still give you 14. Okay, this is your total detector reading. That one is also called your background intensity or your background reading. So in your case here, when you want to process these final readings here into the actual reading, you need to minus off the background intensity. Okay, you need to deduct it off. So if my background intensity is 14, for example, I will have to say 26 minus 14 is 12, 17 minus 14 is 3, 20 minus 14 is 6, and then 35 minus 14 is 21. Then after that, the last step I would need to do is that I need to divide whatever values that I have here by 3. Why do I divide by 3? Is because I actually scan an additional 3 times. 1, 2, 3. There's an extra 3 times I scan. So my reading is actually an extra 3 times. So I need to divide by 3. Then once you divide by 3, you will get your answer already. 4127, giving you the actual reading in one slice. So this process you repeat for the other slices before you're able to build out a 3D image. Okay, so this one, just always remember this. Minus background intensity, divide by 3. Background intensity is always your detector reading. Okay, the total of each set of detector readings. Okay, yeah. Okay, when you do the scanning, it's usually only in 4 directions. You may be asking, why is it that we don't scan here, 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 and here? Now, if you scan here, it's actually just a repetition of what you're scanning here because they are symmetrical, you see. Whatever you're scanning here will actually be the same as what you're scanning here. So there's actually no need for you to repeat your scanning here. You only scan the first 4 set of direction. You don't continue scanning all the way or full round because the slice is symmetrical. You need to scan half only. Then that one would be okay already. All right. So this one is how you go and produce an image. So let's just go do some of the questions just to be clear on what we just learned. If you have a look at page 22, just have a look at page 22. Have a look at page 22 of your worksheet. Okay, this one is actually similar to what we've just done just now. This one is number 17P41, question 9, isn't it? Okay, so describe principles of CT scanning. So image of one slice is taken at different angles to give a 2D image of the slice. The process is repeated for many slices to build a 3D image of the whole structure. This one you can actually recopy back the same points from page 30, I think. Okay, the points are the same. Okay, in your case, that time, your same question with the same set of answer was worth 5 points, right? Here is only worth 4 points. Sometimes for the same questions, they may sometimes change the marks allocated. All right, so don't worry so much about that. Just memorize a single standard answer that has all the points, and then just reproduce it each time you see that question. It is bound to hit all the points one, right? So don't bother so much about the fact that it's 4 points here. If you take the standard answer from the 5 points and you put it here, you're already hitting all the points. Okay. Now, in the other older past year questions, which talks about principles of CT scanning, these were the other points that they would have used. Okay. The process is repeated for many slices to build a 3D image of the whole structure. The resulting image can be viewed from different angles or rotated. This one would have been another point. Okay. Right, so you may see that for certain questions like this, there are actually many points, but they won't be using all the points. They'll just say pick 5 points. Let's just say if this one was like now you see here there are like 6 points, 1 2 3 4 5 6 points here. Some questions marking scheme will just say pick 4 points out of the list of points that they listed here. Okay, so just memorize, as I mentioned, just memorize the standard answer and then just reproduce it. Okay, when the marking scheme they want to mark, they will just see the points. If you give more than required, it's fine. They will just pick the ones that are applicable. Okay, right, so this one is page 22. This one just copy back from page 30 and just add this additional statement. The one that will be more relevant to what you've just done is page 23, the one on the next page. Okay, so this one I don't think there's any issues here. You just need to look at page 23, the page next to it. Okay, now this one they tell you a student creates a model for CT scanning. A section is divided into 4 voxels with pixel numbers A, B, C, D as shown in figure 9.1. Okay, the section is viewed from 4 different directions. It's scanned from 4 different directions, V1, V2, V3, V4 as shown in figure 9.1. Now the detected readings in each directions are noted and then summed. The result is given here. Okay, so what they've done is that they scan in 4 different directions, they add up the values inside the voxels, and this is the final reading. The process that they use is exactly the same as this process here that I just described to you. Originally, they do not know what is the value inside the slice. They need to just scan in all the 4 directions first, find out what is the total value before they can process and find out what is the actual value. Okay, so this one that they have here is actually this part of the process where they really scan all the directions and add everything up. Okay, then after that they tell you the background count is 26. Find out the pixels numbers A, B, C, D as shown in figure 9.1. When they ask you to find out the pixel numbers A, B, C, D, they're asking you to determine what is the actual values of the readings inside this slice. So as I mentioned to you, the standard working would always be to minus off your background reading, then divide by 3. In your case, your background reading, they've already told you is 26. Okay, so you just take whatever values that you have here minus 26 and then divide by 3 as your last step. You'll get A as 7, B as 11, C as 2, and then D as 6. Okay, so the method is always the same when it comes to this kind of questions. Minus background reading, divide by 3. I think I also wrote it somewhere here in here. Yeah, voxel reading is final reading minus background reading, divide by 3. This is the standard step. Okay. Background reading can change from question to question, so be careful of the value. It's not always 26, it's not always 13. It will vary from question to question. But the divide by 3 will always be same. Okay. Now, even though the question never gives you some space for the working, I would suggest that you do the working. Because the marking scheme wrote something really weird. Evidence of subtraction of background, evidence of division by 3. They want to see the evidence of you having done that. If you just wrote this, how would they know the evidence? So it's a bit misleading here or a bit confusing here. So I would suggest you always show the working so that it is very clear that this is your working. Okay, right? So that one is one example here. Okay, then I would have to go to the other questions in the separate sheet that I gave to you just now. Okay, these kind of questions don't come out that often, all right? Right? They come out a few times only over the years. But when it does come out, please make sure that you know how to do this. Right? The separate sheet of paper that I just gave you is actually examples of this kind of question that they have asked over the years, right? From the earlier years. Now, if you just look at that sheet of paper that I just gave you, if you haven't printed it out, never mind. I'm just going to go through the workings with you just so you reinforce what you've just learned. Okay, this one here is medical imaging. Give me a second. I need to open up the past year. A2 medical imaging. Okay, right. Okay, now they tell you a simple section through a body consists of 4 voxels as illustrated in figure 10.1. This is the section, this is the direction of viewing. An X-ray image of the section is obtained by viewing along each of the directions as shown in figure 10.1. The detector readings in each direction of viewing are summed to give you the pattern of readings here. For one direction, the total of the detector readings is 16. Okay, so when you look at this one here, they tell you the detector readings for each direction are already summed to give you this. This refers to this that you have done, where you, this is this part here, sorry, this part here is you having done this part. Okay, then after that, what they want further is they tell you for any one direction the total of the detector readings is 16. Now the total of the detector readings is 16 in any one direction. This one, when you read it, you should have understood that it's actually talking to you about your background reading. Remember just now, if you refer back to this part of your notes, I told you your background reading or your background intensity is actually your total detector readings in any direction. In your case, it is 14 here. No matter which direction you choose, the first one, second, third, and fourth direction, your total detector reading is always 14. This is your background reading. So same thing here, when they tell you about this one, they tell you for any one direction, the total detector readings is 16. This is actually referring to your background reading. So they tell you for the pattern of readings in figure 10.2, state the magnitude of the background reading is going to be 16. Okay. Wait, let me just see this one. This is page 549. I better just show you the answer only. Hey, wait a minute. This is page 549, but I don't have 549 here. Wait, something is wrong with my question. Oh, 549 is here, sorry. Okay, so total detector reading is 16, background reading is 16. Then after that, on figure 10.1, mark the pixels for the 4 voxel section. On this figure, they ask you to mark out the actual reading. So as I mentioned to you, always take whatever readings you have minus the background, divide by 3. So here you get 3, 2, 5, 6. Okay, so same like before. Okay, so this one is 1 example question. Then if I go on to the second one, this one is page 565. You again have something similar, but let's just go through that. Okay, now you also have another similar question here. A simple model of a section of a CT scan is as shown. The model consists of 4 voxels of pixel numbers A, B, C, D. The voxels are viewed in turn along 4 different directions, D1, D2, D3, D4 as shown. Okay, and then they tell the total pixel reading is each of the 4 directions are noted. The total pixel reading in any one direction is noted. Okay, the pixel readings for all the directions are summed to give you a pattern of reading shown. Now, this one that you have is the total detector readings, is the total reading in all the 4 directions. Then they tell the total pixel reading in any one direction is actually talking about your total detector reading in any one direction. In any one direction. This one you could identify is your background reading or background intensity. Okay. So state the background reading in this model, you know it's 19. Find out the pixel reading, the actual pixel reading, same thing, whatever you have here, minus background, divide by 3. So you get 2539. Okay, now where this question will not differ is here. Alright. They ask you, after you have found your answer here, find out your pixel readings along direction D3, along direction D4. Okay, from what you have determined here, find out the detector readings that you will get in directions D3 and D4. D3 and D4. When they ask you to find the detector readings in direction D3 and D4, they're asking you, if I scan in D3, what should be the reading along D3? If this one was the transmitter, and then this one was the detector, what is the reading in the detector here in D3? And then likewise, if I scan along D4, what is the detector reading along D4? So just now we've actually gone through a bit on the process, right? If I wanted to scan along direction D3, which is this one, whatever I have here is the sum of this one. It will be 14. Whatever I have here will be the sum of this one, which is 5. So the detector reading in direction D3 will be 5, 14. Okay. How about in direction D4, which is this one? This one was D3. If you're talking about direction D4, which is this one, so what will be the detector reading here? if you look at this one here, this one would be 2. This one will be 2. And then you're talking about this one going to here. This one will be 5 plus 3, giving you 8. And then lastly, this one here will be giving you 9. So your detector reading along direction D4 will be 289. Okay, so 514 and 289. So far so good, right? So that is how you do this. And then I think there's just one last question there. Then after that I can move on. Okay, the last one is this one, page 573. This one, I'll just breeze through it, okay? Because you'll notice that the questions are the same again. Okay, now in a model for CT scanning, a section is divided into 4 voxels. Pixel numbers PQRS of the voxels are shown. The section is viewed from 4 different directions, D1, D2, D3, D4. The detector readings in each direction are noted. The detector readings are not summed up. The background reading is 34. Then determine the pixel numbers PQRS. Now this one is very, very straightforward already. They've already told you the total number sum up in all the directions. They've already given you the background reading. They want you to find the actual reading now. So it's just a simple matter of taking these values in each voxel minus 34 divided by 3. So you get 5, 13, 9, and 7. That's all there is to it. Okay?